Now, based on your observation, which switch should be on longer to generate water in the second water tank? Once again, the answer is A. Because based on the demand, the turn-on time of switch A should be longer than switch B. Eventually, we can see that the duty cycle is directly proportional to the demand. Lastly, let's consider the voltage equation of the boost converter. If Vs is equal to 40 volt and we apply duty cycles of 0.6 and 0.3 respectively, based on the output voltage values, we can verify that the output voltage is directly proportional to the duty cycle as well. Lastly, we will consider another circuit topology of water distribution systems to represent the buck boost converter operation. Once again, take note of the new location of both controllable and uncontrollable power switches. According to the consumer's demand, System A will perform the buck function while System B will execute the boost function. When switch A and B are turned on, we can see there is a direct connection between the utility and water generated tanks only. Hence, this condition is similar to the operation of the boost converters when the transistors are turned on. However, when we look at the water volume generated by the water generated tanks, we can see these systems are using a different approach. Instead of generating an additional volume of water, these water generated tanks have a similar water volume to the consumer tanks. The reason of this condition will be answered when the switch A and B are turned off. As you can see, when both switch A and B are turned off, the consumer tanks only connected to the water generated tanks only. The water generated tanks will be the sole water supply to the consumers. That's why the water generated tanks need to generate water equals to the consumer's demand. Based on the connection between the water generated tank to the consumer tanks, it is similar to the connection between the inductor to the resistor in a buck converter operation. However, throughout the system operation, we can see there is no direct connection between the utility tank to the consumer tank. Therefore, in the DC converter circuit, you will see there is no direct connection between the load and the DC supply whenever the transistor is turned on or turned off. Therefore, the converter is also known as the indirect DC-DC converter. However, as similar to the previous converters, the duty cycle is always directly proportional to the demand. To perform the step-down function or buck operation, the duty cycle must be less than 0.5, and to perform the step-up or boost operation, the duty cycle of the converter must be higher than 0.5. I will end this video with the comparison between all DC-DC converters. As we can see, all converter circuits have the same components except the connection of power switches. If these converters operated using the same DC supply and duty cycles, we can see the buck converter has better performance than the buck boost converter in producing the minimum output voltage values. Similarly, the boost converter shows better performance in producing the maximum output voltage than the buck boost converter. Nonetheless, the margin of the minimum and maximum output voltages are considered small. Thus, this issue can be neglected. In the next video, we will discuss how to derive these voltage equations.